Hello, good day everyone. Hi, my name is Antoinette C. Pahano of PSECE 3A, and today I'm going to discuss to you a certain topic for my performance task number 11, which is one of the code division multiple access variants, and that would be MC-CDMA. So that is stands for multi-carrier code division multiple access, which is a multiple access scheme used in OFDM based. What we called for OFDM is it is an orthogonal frequency division multiple access based telecommunication systems, allowing the system to support multiple users at the same time over the same frequency band. Moving forward, additional information here about MC-CDMA spreads each user symbol in frequency domain. So that is each user symbol is carried over multiple parallel subcarriers, but is phase shifted, typically 0 or 180 degrees, according to a code value. The code values differ per subcarrier and per user, and the receiver combines all subcarrier signals by weighing these to compensate varying signal strength and undo the code shift. So the receiver can separate signals of different users because this has different code values. Example, it's orthogonal. So since each data symbol occupies a much wider bandwidth, which is in hertz, than that data rate in bits, a ratio of signal to noise plus interference is less than 0 decibels is feasible. So that is for CD-CDMA. And why is it important? So wireless radio links suffer from frequency selective channel interference. If the signal on one subcarrier experiences an outage, it can still be reconstructed from the energy received over the other subcarriers. And also in the downlink, one base station transmitting to one or more terminals, the MC-CDMA typically reduces to multi-carrier code division multiplexing, where all users' signal can easily be synchronized and all signals on one subcarrier experience the same radio channel properties. And also the alternative form for multi-carrier CDMA is called the MC-DS CDMA or MC/DS CDMA, which performs spreading in the time domain rather than in the frequency domain in the case of CDMA. For the special case where there is only one carrier, this reverts to standard DS CDMA. And also there are equivalent ways to describe MC-DMA, right? For example, first one here is it's a form of CDMA or spread spectrum, which is what we have just discussed a while ago. It's also a form of direct sequence CDMA, but after spreading, a Fourier transform is performed. Also, MC-DMA or MC-CDMA is a form of orthogonal frequency division multiplexing according to the definition a while ago that I presented. And yeah, sometimes also called CDMA dash OFDM. So also fourth here, it's a form of direct sequence CDMA, but our code sequence is a Fourier transform of a Walsh-Hadamard sequence. And lastly, it's a form of frequency diversity where each bit is transmitted simultaneously on many different subcarriers. And each subcarrier has a constant phase offset. The set of the frequency offsets form a code to distinguish different users. And next, these are the figures that I'll be showing to you all about multi-carrier code division multiple access. Here, first figure, it's a possible implementation of a multi-carrier spread spectrum transmitter. So where each bit is transmitted over n, here is n, different subcarriers. Each subcarrier has its own phase offset, determined by the spreading code. Next figure is an FFT implementation of an MC-CDMA base station multiplexer and transmitter, where the MC code division multiple access system allows simultaneous transmission of several such users' signals on the same set of subcarriers. In the downlink multiplexer, this can be implemented using an inverse FFT and a code matrix. This one is a code matrix, and this is the inverse FFT. And for the figure 3, it shows a possible implementation of a multi-carrier spread spectrum transmitter where each bit is transmitted over n different subcarriers, and where the above transmitter can also be implemented as a direct sequence CDMA transmitter, one in which the user signal is multiplied by the fast code sequence. However, the new code sequence is a discrete Fourier transform of a binary, say, Walsh-Hadamard code sequence. So it has complex values. So this is the Walsh-Hadamard code vectors showing here. This is the inverse FFT and user signal coming from here, going to this part. And the fourth one is an alternative implementation of a multi-carrier spread spectrum transmitter using the direct sequence of principle. This is the last one. So what are the advantages of MC-CDMA? So if comparing to the direct sequence or DS-CDMA, DS-CDMA is a method to share spectrum among multiple simultaneous users. Moreover, it can exploit frequency diversity using a rake receiver. And however, in a dispersive multipath, DS-CDMAs with a spread factor n can accommodate n simultaneous users only if highly complex interference cancellation techniques are used. In practice, this is difficult to implement, where MC-CDMA can handle n simultaneous users with a good BER using standard receiver techniques. And also compared to OFDM or orthogonal frequency division multiple access, to avoid excessive bit errors on subcarriers that are in deep phase, OFDM typically applies coding. Hence, the number of subcarriers needed is larger than the number of bits or symbols transmitted simultaneously. And MC-CDMA replaces this coder by an n times n matrix operation, where our initial research revealed an improved BER. So to summarize all that I did discuss to you guys, so first, of course, the definition or what MC-CDMA means, which stand for multi-carrier code division multiple access, the advantages, the equivalent ways to describe it, and also figures which will help you to better understand all about MC-CDMA. And I hope you have learned something from me today, and I will see you on my next video. Goodbye.